بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولا و نعم النصیر. Today we will continue our discussion about redundancy in the nature and redundancy resolution schemes. As we talked last session, in many designs in the natural design of biological design, you see redundancy in the number of actuation or in the number of joints to perform a task. For a 6 degree of freedom motion with the arm, we have 7 actuation scheme or 7 joints considered in this kinematic structure. Or for a shoulder manipulator that has 3 degrees of freedom motion, it has usually 4 muscle groups, 1 degree of actuation. In the neck, you will see for 6 degree of freedom, for the mammals, you have 7 vertebrae, but in the birds, this redundancy will include to 14 vertebrae. And this is very particular to of course, it should be beneficial to have extra actuation degrees, and in human wrist, we consider 8 bones for a 3 degree of freedom motion that we require in a wrist. Now, how we can resolve and use this degree of redundancy is a very, very interesting research topic that I will give some examples to provide you the avenue that you can work in this field. For such a system that we have the number of actuations or the number of joint variable exceed the number of task variable, if Q is greater than X, the dimension of Q is greater than the dimension of X, you will see that this robot has more degrees of freedom than 6, the usual 6 degree of freedom in the task space. And the Jacobian matrix is a fat rectangular. It is somehow fat rectangular. The number of the columns are more than 6. If you have only 1 degree of freedom, we have 1 more column. And if you have more redundancy degrees, then we have more number of columns in the fat rectangular. And how we can find the solution, the important is if you increase the number of joint space, or you come to the redundant manipulator to achieve to a certain pose, to find a certain X or X dot, you have infinitely many solutions. You can reach to that point with many solutions, with many different solutions. I can be in here with different configuration. The joint space could be here, consider this is fixed, and the joint space could be differently. And this helps us to increase the dexterity and to do some other work. We can not only reach to the required position, the bird can not only look at the predator, but it can quite fastly look at that, or have different configuration to do that. This means that for such an equation, if X is given, the number of Q would be many different Qs, and usually we can have an optimal Q to do that. Among this infinite number of solutions, we pick one solution which is usually in some sense it is the best, and in some sense means that we can have some optimization cost function to minimize. The basic solution, the very easy solution and easily find solution, which without any problem you can find that with just linear algebra, is the minimum norm solution or the least square solution. We call it the least square solution or the minimum norm solution. This is the pseudo-inverse solution. But in terms of optimization, it does something especially this minimum norm solution. Of course, you should follow that in a linear algebra course, that how the minimum norm solution will optimize the norm of Q dot. It means that basically we have many different Q's or Q dot in the Jacobian inverse solution. We have infinitely many Q dots and to reach to a particular speed at the task space X. So we choose the one if we use the minimum norm solution or the basic solution we call it. We use the Q the norm of Q dot. We use the solution Q dot that the norm of it, the two norm of it, is minimized. This is a very good solution because with minimum energy that we are actually using our actuator, we can get to that point. If I would like to give some maybe naive other methods, maybe suppose that we have 7 degrees of freedom and 7 degrees of actuator or Q is 7 and for a 6 degrees of freedom robot. One simple solution is that just use the 6 first joints to reach to that point, because then it would be 6 by 6 and then the solution is unique. Of course, this is a solution, but this is not a very good solution because you're not using the extra degree of freedom that you have. This basic solution is much better than something like that, but still it may be not the best solution. We can find other best solution. I will talk about that. But this is in terms of the energy that we are using to reach to that point is minimal. The two norm of Q dot is minimum to reach to that X dot. And this doesn't require any sophisticated nonlinear programming or nonlinear optimization. That can be very, very easily found by the pseudo-inverse. We call it right pseudo-inverse because as you see in the last chapter and 2 previous slides that for under-actuated solution also we have some pseudo-inverse that would be left pseudo-inverse. This is right pseudo-inverse. The right pseudo-inverse will find by this, we use this cross notation here. This is not a usual inverse. This is a pseudo-inverse, and the pseudo-inverse is doing that. We use the JJ transpose, the old JJ transpose that we discussed before in the dexterity problem. JJ transpose, regardless of the degrees of redundancy that you have, is a 6 by 6 matrix because we have a fat matrix multiplied by the J transpose, which is a tall matrix. It becomes a 6 by 6 square matrix. And this is, for sure, it is invertible. Since we have more degrees of freedom, we are avoiding the singularities here. In many general cases, this would be invertible. Of course, in some particular cases, this could be even still singular, and this solution does not exist. But since we have 1 degree of freedom, JJ transpose is much more invertible compared to the J as 6 by 6 J matrix. And this inverse is multiplied J transpose from the right side to the J transpose, and then this gives inverse solution, the Jacobian pseudo-inverse Jacobian, that can be multiplied by a 6 by one vector, the velocity vector in the task space, and the total thing would be more m by one vector that gives you the least square solution for the Q dot. This JJ transpose inverse and this pseudo inverse has a very useful properties. You can find it in any algebra, in a linear algebra book, and a short review of that is given in my parallel robot book in the appendix. I encourage you just to read that. It is very quickly given the detail of the properties of this. As you see, for example, J pseudo inverse is equal to I is like a usual pseudo inverse, and you can prove that quite easily, that if you just multiply a J to this one, this would be JJ transpose, and this is JJ transpose inverse. So it will result into unity matrix I. Of course, there are some other properties that you can use to manipulate that. I don't want to go through that linear algebra. I would like to go to further work on that. So this is one basic solution, but this is not the only solution. There are so many, infinitely many other solutions available. And this many infinitely other solution can be found, the set of all solution can be found by this basic solution added by a null space solution. This would be given I plus J inverse J or J pseudo inverse J times any arbitrary vector B. And since this is any arbitrary vector, we have many other solutions here. But this I minus I J inverse J or J pseudo inverse J has a particular property that we can see that this will provide the null space of the J in terms of linear algebra. You are familiar with the null space. What is the null space? The null space means that all the vectors in the form of Q dot n, all this part of vector I minus J inverse J times B, for any arbitrary B, for any non-zero B, this will give you a vector, we call it Q dot n, the new vector or the null space vector, lie in the null space of the Q, of the J. And what is the null space of the J? This means that although Q is this Qn, the Q that is found from this solution, not any Q, but the Q that is found from this solution, is in the null space of the J. This is non-zero, but when it will be multiplied by J, gives you zero solution. It doesn't change the X dot solution that we have already found by the basic solution. So Q dot n is not equal to 0, but when we multiply it by the Jacobian, since it lies in the null space of the J, it will give us a 0 vector in the task space. So this means that this is mathematically very simple and very intuitive to find a null space solution. But in terms of robotic, we call it a self-motion here. The meaning of that is that, again, if I provide you with the figure here, suppose that we have the redundant manipulator here and we would like to move here. If we have a null space, if the system is redundant, then not only this solution works, let me work with that. Not only this solution works, but we have other solution that doesn't change the end effector motion. We have other positions that we can get to the same solution And this is self-motion. It means that if I fix here, there are some self-motion that I can do with my hand. And this is because of the redundancy that I have in my kinematic structure. If the system was 6 by 6 and I fixed the endpoint, then all the solution, there would be only one solution. There is no self-motion. We call it a self-motion. As you see, the self-motion means that you are fixing the last point. If x dot is equal to 0, no velocity, new velocity is given there. There are some motion in the workspace, that in the Q space, that you can get that the same old solution. Please give any interruption and a question if you have. Just I would like to for you to understand the details of this specific problem quite well, and it is very interesting in my opinion, because it has a physical representation, very, very good physical representation for a very well-known problem in the linear algebra. The null space is quite known, and you know that how you can find the null space and how to use that. But when it comes to the picture of a Jacobian, this means that you have a non-zero Q that provides you no motion at the end effector. So this is the self-motion problem. Now, how to do that? What we can say, but the problem in here, as you see, the B is arbitrary, and we have so many B's. How to find the B? This can provide us a freedom to optimize this. The inverse solution for redundantly actuated robot, least square solution, is always the first and basic solution if we don't have any other objective in mind. But if you have some other objective in mind, we call it redundancy resolution. Resolving this redundancy in a form that we get something optimal, something good for our case. And this means that finding suitable Q dot n, this particular null space part of the J, to accomplish some other objectives. What objectives could be done? It could be obstacle avoidance. The problem starts with this. So if we have a self-motion, if we are moving into here and there is an obstacle here, we can use a self-motion to avoid the obstacle, not to hit the obstacle, since we have other solution available. Or maybe the most significant part for our case, representing our previous work, is to circumvent the singularity. For a non-square, for a square Jacobian, we might have some singularities. We saw that there are some singularities in the structure. And we can, if these singularities are within the workspace of the system, which in several times it can happen, we can avoid the singularity. We can move far from singularity, and that means that we have a better motion with smaller joint angle velocities. We can increase the dexterity. This is more important in the bird example that we have shown you. If you have more degree of freedom, 14 actuators for a 6 degree of freedom, 8 extra degree of actuation, then you are very dexterous, and you know dexterity means quickness. Dexterity means that you can move faster, and move faster is very important to be alive in the nature. As you see a bee or a fly, you can never get the fly with your hand because it is quite fast. Of course, I don't say never. Never say never. It is very difficult to do that, to catch a fly because it is dexterous. Of course, we are dexterous too, and with some practice, this dexterity will work. That's the way the nature works. Birds are, the neck of the birds are quite dexterous, but there are some other predators that are more dexterous than that, and they can get the prey for themselves. So increasing dexterity means that if we can change the structure to a redundant structure, and we can use better action. Since I have a network problem, and this is good because it gives the interruption. I was talking too fast maybe, but you see that this redundancy resolution, we were talking about the redundancy resolution, and this redundancy resolution can be done to find some objective like obstacle avoidance, singularity circumvention, increasing dexterity or manipulability, and we defined some measure for these to some mathematical measure, and also some other aspect like we have limited actuated torques. So how can we work with a limited actuated torque there? Of course, if you have only 1 degree of redundancy, you cannot have all these optimization objectives being fulfilled. You can do one more particular case. But if you have more than 1 degree of freedom redundancy, 3, 2, 3, 4, or even 8, as you see in the neck, you can have up to 8 other objective, bringing it into account, and use all the effort or all the power that you have, provide with extra actuator into your system to the problem. And this is a very simple optimization problem. What we can do, either one of that or a combined objective like that, we should somehow define that mathematically and provide it into an optimization problem. So redundancy resolution is solving an optimal problem, and this optimal problem we can define it this way. I have done it just the most sophisticated optimization problem here. I didn't go step by step because we don't have time, but you can follow the chapter of my redundancy resolution in my parallel robotic book. It gives you some more definition and stepwise work in this routine. Some more detail about the solution ways and MATLAB solution for that. So by optimization problem, now we have, for example, at least 1 degree of redundancy. We can have 1 degree of optimization or 1 objective to come into the picture. How we define that? We define that by a minimization or a maximization problem. Find the minimum of V. V is a cost function. We call it a cost function. The optimal objective that you have, the optimal objective should come into the picture with a mathematical representation. For example, the least square, if you use the least square optimal solution, the cost function was just simply the 2 norm of Q dot. But you can have any type of minimization. For example, you remember that we defined mu as the dexterity measure and also arcand as another dexterity measure, and we find that if arcand is similar to there are difference between item 3 and 4 in previous 3. What is the difference? Yeah, we have different type of measures. here you see manipulability and dexterity. For example, dexterity can be used archon. I was talking about that. You can use a measure for dexterity. There are many different measures for dexterity. And you can use other measures of this dexterity. If you use mu here, mu should be close to 1 or very far from 0. So you can use the logarithm of mu as a measure. Then when it is smaller than 1, it becomes negative and then positive. And then you should have some minimization and absolute value of that, or mu minus 1. Something you can consider that in the V that this represents maximizing the dexterity or maximizing the manipulability measure. Of course, the usual routines use the minimization here. If you want to maximize that, you can just find the negative of the cost function that you would like to maximize to find the minimum of that. Anyways, V could be anything, either in task space or in the joint space. And usually we consider this would be somehow Jacobian dependent, because you saw that many of the issues like singularity, dexterity, and manipulability is dependent to Jacobian. Of course, obstacle avoidance is not like that. And for obstacle avoidance, we should find another way to do that. And this is also not very difficult to find. If we know where is the obstacle, we can find the 2 norm of the distance of the robot to the obstacle as a cost function. I will give some example to you to show that how this can be worked. So we should define some particular cost function. Consider that you're optimizing this cost function. You're getting the better solution for this particular cost function. So this is only optimal for that case and not for a general. When we call an optimal solution or optimization, this doesn't mean that this is the best solution. No, it is optimal in a sense that it optimizes, minimizes this cost function. Of course, not only we should optimize that, we should handle the problem, the kinematic problem, correctly. What does that mean? We should have these 2 particular equations being run, meaning that x dot or chi dot should be the Jacobian q dot. The relation between q and x should be determined by the Jacobian. This means that when we are solving for q or where we are solving for x and q should be entangled to each other by our kinematic structure, and the kinematic structure are defined by the Jacobian in the velocity space and by the forward kinematic in the joint space and the task space form. So we have this Jacobian, we should have this Jacobian beforehand, and forward kinematic beforehand, and these are 2 equality constraints. And if you know about the optimization routines, they are very difficult to find an optimal solution with an equality constraint. But this is usually done. At least you have to do to increase that. So you have that with these 2 together, all together. And then when you have this and this, this means that we have the forward kinematics and the Jacobian relation. We have the kinematic structure of the robot comes into the picture. Is the robot a 3x3 robot? It is a serial or parallel? It is a rotational or prismatic? How this comes into the picture? It doesn't come to the picture with the V, because V is the objective that we want. This comes into the picture with these 2. And we can have also some bounds. some upper bound and lower bounds. For example, Q's could be between two things. Q dot could be between the minimum and maximum values, and these Q, all of them are vector. You know, they are not just one Q. We have a number of Q's. We have a number of Q dots, and also the final thing that we have here, if we have some limited torque actuation, if we can bring the torque actuation as a mathematical formulation here, we will discuss about that in our dynamic problem in next chapter. That is also quite possible to do. Then we can have this, of course, being done here. As you see, we are optimizing one thing with some constraint. This constraint shall be done. This is quite possible to do if you have redundancy. And if we add extra bounds, if we add Q smaller than this or Q dot smaller than this, it might need more degrees of redundancy. Maybe with 1 degree of redundancy, we can only solve for one optimal request, not for many optimal requests. I will show you the examples that somehow if you have this and this all together, then you need more than 1 degree of redundancy to solve that. And we shall solve this problem to find the redundancy, the redundant solution to our problem. And this is a very wide range of research. What I can say is that the first IEEE transaction paper that one of my students and I could publish years ago was regarding this optimal solution, of course, an analytic or iterative analytic solution for that. We can have analytical solution for that. It is quite hard. The analytical solution goes with this equation, and finding that, you can search into my papers to see how that works. But usually, and this analytical solution requires a knowledge of optimization course that is usually offered in the electric department, the control department. We have the convex optimization course, and usually we need the Lagrange and KKT multipliers. It is a long story. I cannot go through all the details. The interested people could see the any convex optimization book, especially the book by Boyd is very good. And if you would like to see it in brief, you can go to the redundancy resolution part of my parallel book to see how this is work. And usually we usually use numerical solution. In numerical solution, there are many numerical methods defined there. Interior point method is one of the most significant and most interesting solution for that. And you can use very different algorithms. The AI-based algorithm like genetic algorithm, PSO, and so forth and so on to find this optimization. Or I prefer to have some gradient-based method like the interior point or other method. We call it, and we can use that in the fmin-con function in MATLAB. I encourage you to read about that. Anyways, the problem is not solving it. There are many methods to solve that. The problem in robotics is to define this optimization, to find the usual V, the good V that we can have in here, to define the limitation that we have in here regarding the specific problem. And I will do that in a few examples that in the next slide. So I brought to you this slide was not complete. This is just completed now, you just go to the help of MATLAB for fmincon, and I encourage you to use this function. Of course, there are many other functions available there too, but this fmincon is very, very similar to what we are doing. Basically, to minimize this an fx, a function of x. This x could be q dot, or both of them, or chi dot, both of them. It could be in task space or in joint space, such that we have inequality, non-equality constraint, Cx smaller than 0. Of course, with this equality constraint that we defined for you, this gives us equality constraint for the Jacobian. This could be any function, any nonlinear function. Forward kinematics can come into this function in terms of equality constraint. It could be a linear inequality constraint and linear equality constraint. This is the Jacobian case that we have. We use this one for sure, and then we can have upper bounds and lower bound for x, or upper bound and lower bound for any function of x that we can increase that. And you can define the function and all the details, and also the options is very important. Go through the details, and I will give you an example, a sample example for that I have written for the problem that we discuss in here. And you can use different algorithms. The algorithm is set to interior point. As I mentioned, it is maybe the best method in a sense that it is quite fast and quite rigorous, but you can use trust region, SQP active set, SQP legacy, different other algorithms by defining the option in this function, in the MATLAB function, and you can find the solution. Usually for regular problem, it is not a big difference to use different regions. The only difference would be the time of convergence, but particularly in some particular cases, then we come to ill conditioning and so forth and so on. It might be some method could give better result, and some method cannot solve the problem. I recommend you to go with the interior point with the default function, and to use that. Now, before going through the examples, if there is any question up to here, I would be more than happy to answer.
I have two questions. One of them is that do we solve redundancy offline or during the operating flow?
Again, we have your voice a bit. Your question was about running it offline or online?
Yes.
Yeah, we have both of them depending on the queue. If we are designing a desired trajectory for the system, it could be offline. But if we have within the feedback loop of the system, we don't have a beforehand knowledge about the motion of the system, it should be online. And online optimization is very, very difficult, because this numerical solution usually require more than a large time to converge.
Okay. And are dexterity and manipulability the same concept? Or
no, they are the same concept, but if they were the same, they have the same name. They are a bit different. Manipulability is defined by the multiplication. You were not in the previous class, I guess.
Oh, sorry.
It was defined there. Manipulability is defined by the multiplication of the singular values, all the singular values of the Jacobian matrix. But there are, I can say about more than, usually I said 400 other measures. Not 400, but there are at least 10 other dexterity measures, we can call. Dexterity is a bit wider than manipulability. Manipulability is defined quite restrictly by the multiplication of the singular values. But if you have different issues, I don't want to talk about it because it is a large area of research. You can look into the literature about that.
Thank you.
Moin, you have a question. Why you are not asking your question by your microphone? You don't have your microphone active? Yeah, just go ahead and ask your question. به فارسی هم میتونی سوال کنید اگر سوال دارید.
Excuse me, I am just joined as a guest, but
no problem.
Okay, I can ask you. I saw a video that a Japanese engineer was working with a manipulator, and it was in null space, and the end effector was fixed in a space, and the man was freely changing the arm by hand, but the end effector was in a fixed position. My question is that that manipulator was controlled in task space or in joint space. I think
both of them is possible. It can be usually controlled in the joint space. If it is a serial manipulator, it is usually controlled in the joint space. We will talk about that in our chapter 7 in the control part. We'll discuss the difference between that, but it could be either way. The point is not the control scheme. The point is the redundancy scheme. If we have a degree of redundancy, then we can the degree of redundancy, as you see, either in joint space or in task space. Usually for serial manipulator, we work into joint space.
So we have to prevent the null space in control.
We don't prevent the null space, we use the null space. We have the solution here, we find the basic solution, and then we use the null space. We use that, not prevent that. We use the null space. We add some extra Q dot. The self motion is exactly it. We add an extra motion into the manipulator in the joints that doesn't really have any effect on the task space. This means that this is fixed, exactly the video that you have seen. This is fixed and this is moving. This is fixed. Of course, I cannot fix this, but I can not show you here. But now, suppose that this is fixed and then you have some motion here. This is exactly the self motion. We are using the redundancy in our arm to do that. If this was not redundant, then when you fix the end effector, all the joint will be fixed. Exactly, this is the same problem that I am talking about here, and I will show you some example. It could be fixed or not fixed, but when you fix that, it is easier to see the self-motion. The self-motion, again, is a Q dot and a solution, this part, which is not equal to 0. It is a motion in the robot, which is not 0, but the result of that, when you multiply it by the Jacobian, gives you 0 end effector motion. There is no motion for the end effector. And this we call self-motion.
Thank you very much.
Doctor, excuse me.
Yes?
According to your experience, how much we need to perform on online optimization?
It depends. We cannot say. The best way is to avoid optimization, online optimization. But we need it many times, several times. And when we would like to do that, that's why we use analytic solution. If you work on an analytic solution, it is very hard to find an analytic solution, but then running it in online is very good. And also in terms of the method that we are using, SQP method, are very effective for online optimization. We have done that in, of course, for parallel robot, not for serial robot. Serial robot are easier, much more easier than parallel. But for parallel robot, we have done that, and we have solved that both analytically, and we have performed run it online on our cable robotic system. You have to usually, depending, you should wait a bit for our last chapter that we talk about trajectory motion planning and also the control part. That would be seen then what is online and what is offline. Anyways, let me go through the examples. The examples are quite interesting. I can see, you can visualize now. I have talked about the different thing. I will also leave this inverse acceleration for now. You can follow that. You can find the inverse acceleration for non-singular configuration by this equation. But the example that we have are quite illustrative, and you can understand it. Of course, I borrowed that from a book that is given within the books that I provide to you in the course. But I wrote the program myself, and I will provide the programs to you to find this system. The problem is that we have a 3 degree of freedom robot, a 3RR, a 3R manipulator, but a 2 degree of the manipulator motion. This is the simplest possible redundant manipulator that we can have. And the motion, we don't require any orientation. We are not about any orientation of the end effector. We would like to move from this point, Q0, to this point, to 0. As you see, we have a RRR, and this is 1, 1, and 3.3, the values are given. The initial point are given by 20 degree, 30 degree, 20 degree, something like that. And the final point, there is a point here which is almost 1.7 and 1.4 with some degrees of accuracy. And then you would like to reach to this point, to the 0 point, very easily. And you can see, you can feel, since it is robotic, can see if you just move down, you will interfere with the obstacle. It is not easy to move down. It is not correct to just move down. You should do it some other way. And since we have 1 degree of redundancy here, we can use the redundancy scheme to move from here to here, but avoid this obstacle. So the problem is clear. We are starting from this point. You would like to go to this point, but with some obstacle. So in the task space, now Moin asked, we are working in this joint space or task space. Here we have the desired trajectory. We can do that quite offline because we require to have a task space solution. If we consider the X task space variables, we can very easily find 2 trajectories. The simplest trajectory we call here are cubic. I will talk about that later, how to design that. But except for me, X shouldn't be changing in this example. So X desired is equal to X0, the X position, and Y position should be started from Y0, we call it Y0, and then end to 0 in 1 second. Let's say we have 1 second trajectory. We would like to move this in 1 second. And if you put 1 in here, you will see that it will start from here to here. From here, this Y at the time 1, YD at time 1 would be equal to 0, this Q final point that we have. Since we have the desired in the task space, we have the time derivative of that very easily defined with that. We have this, but we don't have the Q's. We have the x and x dot. You can see we have x and x dot, but we don't have the q's. We have two problem. We have two requests here, 2 degrees of motion in the task space, but we have 3 variables in the joint space. So this is a redundant problem, and we can have infinitely many solutions for that. As you see, since we have 2 x and y desired trajectory and 3 q in here, we have 1 degree of redundancy as the simplest possible case in here. And to move the x, that is 2 to 1, 2 from here to here, the q, which is 3 by 1, has 1 degree of redundancy. We have infinitely many number of solution to that. But now for that, we just consider the first objective. Consider that we would like to find the obstacle avoidance. We would like to avoid this obstacle. How to do that? We should define an optimization problem, but the optimization problem, we should find the Q, the V, the cost function here. Many different ways can go how to avoid this obstacle. Could anybody just suggest something that suggests a particular V cost function that if we optimize it doesn't hit this obstacle? It is not very easy for at the beginning, but my intuition is that consider the forward kinematic and inverse kinematic solution. You know that a robot like this has usually multiple solutions, has elbow up and elbow down. If this robot comes with elbow down, it will hit the obstacle. But if it goes with elbow up, it can go from here to here without hitting the obstacle. If we are elbow down, as you see, we will hit this obstacle. But if we go elbow up, I will see here, if we go from here to elbow up, then we don't hit the obstacle. So we try to make it elbow up posture. Robot shall go to elbow up posture to avoid the obstacle. And we give, because this is an optimization routine, we give that QD should be somehow elbow up. Elbow up means that the degree of these two angles should be negative. If this is 45 degree, this should be minus 70 degree or minus 10 degree. It is not very important. These are not very accurate, but the minus is important. If QD is positive, this is positive, this gives you negative. So we say that although we are moving through that, since we would like to define a cost function, we define a cost function, Q minus Q desired. The Q desired is an elbow up position. Your Qs shall go to an elbow up design. So you should minimize this cost function by the 2 norm of Q minus QD. If you find the difference between Q and QD, then it would be much easier to go to that. So notice that this is a not very accurate obstacle avoidance problem. We are just giving a elbow up position. But for this particular example, this will work with a very, very simple cost function. And this is very important. If you would like to solve a problem, don't solve it by the most sophisticated one. Of course, you could consider this distance and this distance from here to here and make it, add that together and have some never hitting this, to increase these distances. But that would be much more difficult, and it is in the task space. Here, I can just use elbow up position in here. So, of course, this is this could be, of course, either of you can find any other objective function or optimization cost function, but it should be subject to two straightforward and strict equality is the constraint. The first equality constraint is that Jacobian should hold. The second is forward kinematic should hold. And if you use that with this cost function, we need the Jacobian. Of course, for 3RR, we have already found the Jacobian. You can go back to the last chapter slide. And also for the kinematic, in the other chapter, we have also the kinematic given here. X1 and X2 is given here, or X and Y. And here, the Jacobian is here. And so we have the forward kinematic as a function of Q, this Jacobian as a function of Q dot, and our V, of course, V is only a function of Q, doesn't require any Q dot. You can add something to it. And doesn't matter really. The important thing is that to find this VQ. And the rest will solved by the MATLAB, by the F-Min-Con problem. You can see, first, I didn't solve the MATLAB. I used the pseudo-inverse. If you have the pseudo-inverse, you know, you have the X dot here. You see we have the X dot here, X and Y. We have the X dot here. We can use the pseudo-inverse of the Jacobian and find the Q, 3 different Qs that we have in here. And then if you find this by the Jacobian, the solution minimizes the two norm of Qs. And as you see in here, since the norm of Qs are very small, doesn't move rapidly from elbow down to elbow up. And this means that it is a solution. Really, the robot could come from this point to this point with this posture, but there is no obstacle avoidance there. And we know that the basic solution doesn't have the obstacle avoidance constraint in it. If we need the constraint, if we need the obstacle avoidance, we need to use this problem, this optimization problem here. So here is to show this is a solution, a simple solution, but not good for this particular problem. Now, if you go to this, if you just solve this optimization constraint, you go from this with these two obstacles, the desired trajectory, as I mentioned, is an elbow up trajectory, and you solve it for different point here, you can see that very, very fast from the initial condition. At the first step, of course, from here to here, there are transient. I just showed 5 points here. You can show more than that. You will see that because of this requirement that we would like to go to an elbow up, the robot solution will find from infinitely many other solutions that it has, the solution that it is elbow up. So it will goes to elbow up position here, and then you see it will come just down up to here quite easily. It will traverse the trajectory quite accurately with the elbow up, and there is no obstacle collision here, and the system is working quite well. Very, very illustrative example. I like it very much. I hope that you like it too. It is a bit difficult to write the program and find the cost function, but the solution is very easy. If you don't use obstacle avoidance, you will hit the obstacle. If you use a simple optimization routine, you will avoid that. Let me just add another point here. Here, as you see in here, in the optimization problem, we could have some constraint on the velocities as well. Here we don't have any constraint on the velocity. In this solution, we have minimized the velocities, as you see, very, very easy motion. In here, we have obstacle avoidance, but the expense is that we have we should have fast velocity exactly at the beginning. When you start from here, from elbow down to elbow up, you should move fast from elbow up to elbow down to go to the solution. What will happen if I add another constraint here? Remember that we have only 1 degree of redundancy. So we can just solve one redundancy resolution objective here. Now I add another extra term here in the next example. I ask that the Q dot is within a limit. And the limit is somehow the practical limit that we have, 1.2 minus 1.2. Of course, if this is large, for example, 10 or something doesn't happen. But as you see in here, if we have this added to this example, and then again we just run the fmin con problem. I will give you the program. You can work with that program later within your assignment that you can solve for that. You see that if you have this, of course it go to our elbow up as you have, because this is enforcing that, but we don't have the right speed. You will see that since we are limited to this speed, somehow the trajectory will be distorted here. It cannot go quite fast. This means that we couldn't solve the exact problem that we would like to have, x dot is equal to jq q dot, because of this limitation here. And why this is the case? Because we have only 1 degree of redundancy, not 2. If we have 2 degrees of redundancy, then it would be no problem. Of course, it could have some other problem coming into the picture, but here, as you see, we have only 1 degree of redundancy, so without speed limit, we can quite easily avoid the obstacle. But if we have an obstacle and we have speed, then the motion is not as correct as we want. Of course, this is also still acceptable robotically, in the terms of a physical application. But mathematically, it means that this problem is not solvable in all the points. In here, there is no problem. But in the beginning, when we are moving from elbow down to elbow up, then we exceed the speed limit, and we have the problem. Let me explain that in Farsi as well, because it is somehow maybe some important issues there. نکته‌ای که گفتم اینه که ما 1 درجه افزونگی داریم. وقتی 1 درجه افزونگی داریم، یکی از ابجکتیوامون رو میتونیم داشته باشیم، حتما برآورده کنیم. و اگر ما بدون سرعت حد، به اصطلاح حدی یا کرانی در سرعت مسئله رو حل کنیم، ملاحظه میکنید که خب خیلی قشنگ جواب پیدا میشه بدون اینکه برخوردی با این مانع ایجاد بشه. اما وقتی که ما میایم یک شرط دیگه میذاریم، یه خواسته دیگه توی مسئله اپتیمیزیشنمون، مسئله بهینه‌سازیمون اضافه میکنیم، 2 تا خواسته داریم اینجا، هم obstacle avoidance، هم عدم برخورد با مانع، هم رسیدن به محدودیت‌های سرعت. حالا 2 درجه 2 تا ریکوست داریم با 1 درجه ریداندنسی، 1 درجه آزادی اضافه. 1 درجه آزادی میبینید تو بعضی از نقاط به ما جواب نمیده و اون مسیر صافی که مد نظرمون بود رو ما اینجا نمیتونیم طی بکنیم. و این علت این که مهرهای گردن یک به اصطلاح پرنده مثل یک انسان نیست که فقط 1 درجه ریداندنسی داشته باشه، 8 درجه اضافه ریداندنسی داره. تو انسان با 1 درجه اضافه کارمون حل میشه، ولی در پرندگان 8 درجه اضافی خواهد داشت که این مسئله حل بشه و بنابراین ما سرعت‌های خیلی زیادی رو هم اونجا میتونیم در واقع با این ماهیچه‌های کوچیکی که توی گردن یک گنجشک مثلا وجود داره بتونیم داشته باشیم و شما میبینید که چقدر سریع پرواز میکنن و چقدر سریع میتونن در واقع از گردنشون استفاده بکنن برای حفظ زندگیشون و برای به دست آوردن غذا. Anyways, this I think is very, of course you should run the program yourself, you write your program. I will provide my program to you to work with that. And as a final example, I go through the very similar example, but with another optimization constraint. In this example, we don't have any obstacle here, but as you see, we have a program with the same 3-arm example that we have, but the motion is very close to the singular configuration. The singular configuration is, minus, that if we have a fully retracted arm, it is singular. So if the arms are close to each other, if they are very close to each other, then it would be quite close to singularity. If we would like to move very close from here to here, suppose from here to here, it means that we are very close to singular point. We have the same old problem, but just changing from here to here, moving the motion somehow in a place that the robot is in singular configuration. And if you use the pseudo-inverse solution, the pseudo-inverse solution gives you very simple and very slow motion, let's say, or easy motion for the robot, but very close to singularity. Do you see the singularity close to singularity is here? The arms are very close to 180 degrees. They are not singular, exactly singular, because that singular configuration we cannot move, but very close to singular. Can we move this robot from this singular configuration? We know that if we have singular configuration, we need a lot of torques and a lot of speed here. Yes, of course, we can move it from that by adding a cost function which is related to the singularity. Now we add a singularity robot. For example, we consider the manipulability measure. The manipulability measure was the determinant of JJ transpose inverse or the singular values of J. You can use both of them in the MATLAB. You have the singular value and you have the determinant. And this is quite fine. And this is the manipulability measure. And the manipulability measure, if we minimize the manipulability measure, it means that we are reducing the redundancy to some extent. Again, subject to the same particular robot that we have, exactly like the before. The only thing is that the V function is changed. Instead of having optimization that avoid obstacle avoidance by bringing it to the up position, to the elbow up position, here we consider optimization for a particular cost function. And the simple cost function is the manipulative measure. You can use the arcand as well with your cases. And as you see, if we run that, the robot will move away from, as you see, the angles becomes larger than before. Here we are very close to 180 degree, but here the robot will move away from singularity. Of course, it is not moving very far away because the motion is very near to the singular, and you can see that the motion is exactly obtained at all different points. We have the same line in here, but the manipulability measure will now somehow increase in here. Of course, you can use any other cost function to solve the problem within these cases. I just stop in here, and also let me emphasize on the inverse problem in the acceleration as well, because I did very fast, go through this very fast. The inverse solution in the differential kinematic is either a pseudo-inverse or an optimization problem. But if we go to the acceleration of the robot, then the problem of acceleration, then if we differentiate from that, a J dot comes into the picture. Remember this equation. We will use that in the control part. And if you would like to find the inverse, you've given x dot, you want to find the q, you need to have an inverse of Jacobian as well. So for a 6x6, for a fully actuated robot, it is quite easy to find q dot as the inverse of that, and q double dot as the inverse of this equation. That will give you the inverse problem, the acceleration. But if it is not squared, the problem is much more difficult. And of course, there are some optimal solution there, but it is much more difficult, and we don't discuss it in our case. So just my final point, please, I will provide my program, my own written program, which was take a bit of my time. Of course, I'm not a very professional programmer in MATLAB like some of you are, but I will give the program to you to work with that and find work with different other objectives and maybe other robot to solve the problem and to learn how to use the F-min-con in real practice. Yes, Hossein, I have some questions.
Excuse me, Doctor. And
go ahead.
Slide 81.
Yes.
Yes. This configuration, this strict configurations, did we took the constraint of the length of the arms in consideration or not?
The length of the arms are fixed. We have 1.3. If you see at the beginning, 1,
yes.
1 and 2.3. So the lengths are quite fixed. We don't have any constraint on the length.
Yes. Another question, please. Choosing the desired cues. What is the criteria for choosing the desired cues?
As you see here, we have a desired X. We go to a desired Q. The objective is what is the demand in your program. In here, we are avoiding singularity. In here, we are avoiding obstacles. And to give you different cues, we have a motion to be run in the platform. We have robot motion. We need a motion. A robot starts from one place, go to another place. Since it is redundant, we can have another objective here. Another objective here is obstacle avoidance, and in here is singularity circumference. So you have a desired Q to do that. Now you have a Q desired. Does it mean that the robot moves there? No, still the problem is not solved. We should have a control algorithm. We have the desired motion. Now we should have a control algorithm to move toward this desired motion.
Can I have another last question? In reality, we choose we put or we draw a desired Q or a desired X, a desired path or desired the angles.
Okay. Yeah, I understand now your question. Again, we will discuss it in the control part, in the beginning of the control part. But a robot, the demand is in the X we would like to have a trajectory traversed if J is squared. This means if you define the task space, you have one solution in the Q space. That's all. You can find it by the inverse Jacobian. If you know how to go there, you have only one solution in the task space, in the joint space. So that it doesn't go that much different between the task space or the joint space. We usually work in the joint, we control the robot in the joint space. Although we would like to move in the task space, we find from the task space, from X desired, we find the Q desired, and then we control the Qs. What I am adding here is, if you have redundancy in actuator, if you have one extra actuator, one or more, then not only you can have this mapping, you can from one X find there is not only one Q, there are so many Qs. So you can find an optimal Q. The same path, you are doing the same writing, but you can do it this way or this way. And you know that the people with right hand and left hand write differently. Right hand people write this way, left hand people write this way, elbow down and elbow up. And this is because we are redundant in here. The same task space motion can be done by elbow down or elbow up configuration. And this elbow up and elbow down configuration can become from here. Just to finalize your question, first, what is required for us is in the X space, in the task space. But what we control is usually in Q space. So regardless what we would like to have in the task space, we map it in the Q space, and then we work on the Q space, on the joint space. This is officially true for serial manipulator, not for parallel manipulator. For the parallel manipulator, this is exactly the inverse. But for serial manipulator, we work in the joint space. Thank you very much. I guess we are getting too long and very early that time. Zahra has a question. Yes, Zahra, please. Just your voice is still with some delay. Work a bit louder. Yeah, okay.
Do you hear me now?
Yes, it is good now.
I'm saying in this optimization, it looks to me that it's just for finding the inverse of Jacobian in an optimal manner. So I was thinking why we include the kinematic constraint as well.
Very, very good question. Very, very good question.
Thanks.
But very professional. The reason is maybe all the students cannot follow me. Don't worry about that. This is not. When I was writing the program, I didn't put this one here. This is because I write the program myself. I run it. The way that I am talking to you, I should first solve it myself. You know, the problem is our cost function is in Q space. But the constraint is in differential Q. It is in X dot. If you don't put this one here, the relation between Q and Q dot is not confirmed. Q and Q dot should be exactly the derivative of each other. But if your cost function was in Q dot, and this was in Q dot, you don't need this function at all. You could work on the Q dot and find the Q dot, and from the Q dot you can integrate and find the Q. But when you are running a program, your V is a function of Q, and your constraint is a function of Q dot. What is the relation between Q and Q dot? We should define it. How you can define it? By this forward kinematic map. When you have this and this both together, of course correctly, if you write the kinematic correctly and the Jacobian correctly, these are the derivative of each other. X and X dot are the derivative of each other. And then the problem is solved. So you have a problem with a number of, as you see in here, I have written somewhere, a note in here, I don't remember here, you see, the number of states that you are optimizing is not only Q, it's Q and Q dot, both of them. And you have to find this relation to give this relation. You haven't given any dynamic formulation here. So you should give this to both of them in here to find the solution.
Okay, got it. Thank you so much.
Very good. Thank you for your very good question. Thank you all for the contribution you have made, and hopefully we can go forward next week. The week after, we have, unfortunately or fortunately, we can say, we are getting to the 19th and 21st of Ramadan, Sunday, and Tuesday would be basically Tuesday is a holiday, a national holiday, is the martyrdom of Imam Ali, peace be upon him. We don't have class on not next week, the week after. We don't have class on Tuesday, and on Sunday also. It is just the day after Ahya, the night of Ahya, and so that's probably we should change the time of the class somehow that we don't miss that, and probably we have another makeup class for the Tuesday session to make it complete. Please come with me, be with me with the class. Don't be far away, that we can continue discussion as we go along. Good day, and take very good care of yourself. Goodbye.